So this theorem is about two variable function. But in general, we have to consider nth variable function. What should we do? Okay. We have this corollary. If we consider our function is n variable, is a ball or the R neighborhood of A in Rn. Okay, and f is a function defined on this ball. So this is an n-variable function. Okay, so if these two partial second order partial derivatives exist in the R neighborhood of A, and they are continuous. These two are functions of the R neighborhood of A. If these two functions are continuous at the point A, then Fij equal Fji. So this is a generalization of the previous result for two variable function, two arbitrary variable function. Okay. So how to prove this corollary? As a corollary of the theorem, we need to transform this the situation to the case where the theorem can be applied. So we need to construct two variable functions from this given n-variable function f. Okay, how to do this? We consider two variable function denoted by phi given by f phi xy is f a1 ai minus 1 x ai plus 1 aj minus 1 y aj plus 1 an. That is for f. For the n-variable function f, we fix n minus 2 variables. Only let the i's and the j's variable change and denoted them by x and y. Then you can check. We can apply the theorem to phi. This I left for you to check. This is an exercise for you. Okay, so we apply the theorem to this function phi. We obtained Fij is the second derivative of phi, first x and then y, at the point aij. So by the theorem, the differentiation of phi can be switched. First x, then y can be switched to first y and then h. Therefore, equal but this is just Fji. So the corollary is proved. Very easy. Okay. I have to remind you that this, what's this? This is dy d phi dx. So this is y. Although we write y first, here in this notation, we write y first and then x. But actually, the differentiation is first with respect to x and then y. The reason is here. Okay, so although y appear first, but the differentiation is x first. You need to remember this rule. Okay. Now we introduce a very useful notation. We use the capital N to denote the set of non-negative integers. Okay, and if omega is an open subset in Rn, and f is a function in omega. So for alpha 1, alpha n, in the Cartesian product of n, of these non-negative integers, the Cartesian product nn, an element has n component, alpha 1, alpha n, both all the alpha 1, alpha n are non-negative integers. Okay, and also h1, hn in Rn, we denote the length of alpha is alpha 1 plus alpha n, and the h alpha is h1 alpha 1, h2 alpha 2, hn alpha n. This is as the notation. Okay, we defined for alpha and h, we have the length of alpha and the power of h to the power alpha. Also, we have the alpha is alpha 1 multiplied alpha n, and we also use this. Okay, now using this notation, the higher order partial derivative can be denoted very elegant. So d alpha f, what's this? This is d alpha is alpha 1 alpha n, right? So what's this? This is an higher order derivative of alpha. The order is the length of alpha. I will write this. So we take alpha 1 times derivative with respect to x1, and then alpha 2 times derivative with respect to x2, and so on, and the alpha n times of derivative with respect to xn. Okay, so this complicated higher order derivative simply could be denoted by d alpha f. Very elegant notation. So for example, alpha is 1, 2, 0, 2. So alpha has 4 components. This means the small n is 4. Therefore, we are considering 4 variable function. For example, f is a function in R4. So how about what's the d alpha f? For this alpha, d alpha f is the total order of differentiation is the sum of the components of alpha, which is 1 plus 2 plus 0 plus 2, so it's 5. So the total order of differentiation is 5. Here we differentiate with respect to x1 once, because the first component is 1, and to x2 twice, because the second component is 2. So the 2 here means differentiated with respect to x2 twice, and to x3 0, so no differentiation are taken to x3. Finally, 2x4 twice. Okay, so this is an example. So from this example and from our explanation, you should feel comfortable about this very elegant notation for higher order derivative. Okay. Now we have some important notation. So omega is opened. F is a function on omega, and k is a non-negative integer. So if for all alpha which the range is not greater than k, all the alpha order derivative as a function in omega exists and continuous. Okay, in this case, this condition means that all the higher order partial derivative of f until order k, until k order, the order less than or equal to k, all the partial derivative functions are continuous. Okay, then we say that f is k times continuously differentiable. And in notation we write f belongs to ck omega. In other words, we use ck omega to denote the set of all such functions. Therefore, f belongs to this set means that f is one of such a function that is has a continuous partial derivative until order k, including k's order. Okay. So an obvious fact is that if f is ck, then the partial derivative of f is ck minus 1. Okay, this is easily see. Okay, so this is a very important terminology about the smoothness of real valued functions. Okay, now we consider vector value functions. So f is a map from omega to Rm. Then f can be written as f1. F will have m component. Okay, so if all fi are ck, so this we have introduced this notation, meaning that all the component of fi are ck, has a case order continuously differentiable. Okay, then we say that f is ck. This vector valued function is ck, which means it is k times continuously differentiable. Okay, f is ck, and in notation we denote f belongs to ck omega Rm. Okay,